HPCC Systems presents HPCC for Managers, Lesson 7, Using a THOR Cluster. In this lesson, we'll talk about using a THOR cluster, why it is powerful and flexible, how it works, overview of extract, transform, and load in THOR, the individual processes broken down into specifics, a little discussion about payload and non-payload indexes, as THOR is the cluster where indexes are built, ROXY is the cluster where indexes are delivered. The overview of spray to delivery, and then finally the HPCC data factory. Here's a diagram of the data refinery or factory. Again, THOR is also known as the LexisNexis HPCC data refinery. It consists of the following: one master node is shown above, and as many slave nodes as needed to complete the configuration. A THOR cluster is a disk-based, massively parallel computer cluster. It's optimized for sorting, manipulating, and transforming data, and it is specifically designed for ETL, known as the extract, transform, and load process. And it's built to handle massive ETL loads. Three things that give THOR its power are: number one, massive computing power. For example, a 400-way or 400-node THOR may have 400 SCSI controllers, 800 fast high-capacity disk drives, 1.6 terabytes of RAM, and 1,600 processor cores. Another thing that gives THOR its power are high-speed, high-capacity network connections between all of the nodes. We use backplane capacity of the switch, which can currently reach a theoretical 1.4 terabytes per second. And the current non-blocking wire speed in these switches is 700 gigabytes per second. The ECL language is the third reason that THOR is powerful, as it automatically parallelizes any process. It's designed for data applications, and it is transportable amongst varying sized clusters. The code that you write for a 20-node THOR is the same code that you apply to a 400-node THOR. It is extremely portable. Now, how does THOR work? Again, a 400-way THOR has actually 401 execution nodes, the 400 slave nodes, and the one master node. When data is sprayed onto THOR, 400 slave nodes each contain a small part of the data. In total, they make up one logical file that you reference as an ECL programmer. The master node coordinates the work between the slaves. And the extract, transform, and load processes are performed, and indexes are built for index queries using massive joins and merges and massive sorts and transformations. The data is delivered by either despraying it back to the landing zone from whence it came, either kept on THOR to be used again, or copied or pushed to a ROXY cluster. Now here's the overview of the ETL process in more detail. Again, ETL is short for extract, transform, and load. The ETL process can be different for every single build, and a variety of ETL tasks are performed depending on the content and type of build and the number and types of sources. Extract involves importing and cleaning raw data from multiple sources. Transform involves the combining and collating of that information from multiple sources. And finally, load involves producing the indexes for data delivery and eventually to be deployed to ROXY. The ECL IDE is used to write the ECL code to perform any part of the ETL process and develop and test queries, transform data, and indexes. So again, the overview of the extract process is to convert the data into usable formats, which is appropriate for data transformation processing in the HPCC. Also, another part of the extraction phase involves parsing of the extracted data to check if the data meets an expected pattern or structure. And if not, part or all of the data may be rejected entirely and not useful for the transform process. Now, the transform process requires multiple steps, including Mapping and translating source field data into common record layouts depending on their purpose. Some examples include combining multiple records into one, which we call denormalization, or splitting single records into multiple records, which we call normalization. Translating codes into descriptions and or vice versa, making numeric or cryptic codes more readable to the customer, and the splitting of conjunctive names. Also, reformatting and validating date fields to a consistent format is also important. We also identify and append internal IDs to people, businesses, and other entities to link them together across varying data sets. Another reason for transformation is to apply duplication and combination rules to each source data set and the common build data sets as needed. Depending upon the type of source, data sets are processed. All new records will simply be added, existing records may have to be updated, or existing records may even have to be replaced. Duplicates may have to be identified and either excluded or combined with existing data, possibly expanding the valid date range of that data. And finally, linking records to each other is part of the transform process, if applicable, providing timelines of activity or status. And finally, the load process involves building indexes and deploying data and queries to any Roxy cluster. Building an index is primarily a sorting operation, which is why THOR is so good for this process. Indexes built on THOR are usually used on a Roxy cluster for fulfilling interactive type queries. These queries involve rapidly accessing a specific record needed by an individual query, and these indexes that are built on THOR can also be used on THOR or the ECL agent, used for testing prior to deploying to Roxy. Indexes also have an extra file part. For example, in a 400-way THOR, producing an index query where 400 parts contain the main data, and the 401st part contains the top-level key in the index, indicating which of the 400 parts a given record resides in. This is called the key of keys, or the meta key. Now in THOR also we have two types of indexes that can be built. They're called payload or non-payload indexes. Payload indexes contain additional fields as well as the searchable ones, where non-payload indexes or standard indexes only include searchable fields. The index maps a searchable field into one or more results, and in simplest cases, all the fields are searchable and the result isn't implied, is it there or not. In another case, all fields may be searchable apart from a file offset into a raw data file where the result is to be found. For performance reasons, it is often preferable to copy that data into the non-searchable fields of the index so that they can be retrieved using a single fetch rather than two. And this is the technique called the payload index. But payload indexes provide better performance at the expense of disk space. And in other words, when you're including the additional data in multiple payload indexes, there will be redundant data that exists on the Roxy cluster. The result is duplicated in every index rather than shared between them. All right, the last thing on the THOR cluster we want to talk about is called spray to delivery. The three main stages in this process are as follows. Number one, data is sprayed onto a THOR cluster. Number two, the ETL process is completed. In other words, queries are developed and tested, indexes are built, and transform data and indexes are tested. And number three, the delivery of data files created as a result of the ETL process may be either desprayed back to the landing zone for delivery to external customers, left on THOR to be read in subsequent queries, or copied directly to a Roxy for use in interactive queries from a production system. So, in summary, you should now know, first of all, what a THOR cluster looks like, why THOR is so powerful and flexible, how THOR works, and how the ETL process works, know a little about payload and non-payload indexes, and the sequence of events from spray to data delivery. This concludes our lesson on using a THOR cluster. When you're ready to continue, proceed directly to Lesson 8, titled Using the ECL Agent or HTHOR. Thanks for watching.